Good morning, good afternoon, good evening, wherever you're hailing from. Welcome to another edition of Cloud Tech Thursdays here on OpenShift TV. I am Chris Short, executive producer of OpenShift TV, and I'm joined by my fellow Red Hatters, Josh, Mike, and Amy. Mike, I'll hand it over to you for the starting of introductions.
Yep. Hi, everyone. I'm Mike. I'm the Ceph Community Architect for Red Hat.
I'm Josh. I work on cloud native projects here at Red Hat, mainly community support and facilitation.
Amy, I'm the OpenStack community person for Red Hat, and if you are an OpenStack person, you know me as Spots.
So I'm joined here with, or rather, we're all joined here with Jim Blair, who is the project lead for the Zuul project gating system, and is a founding member of the Open Dev collaboratory team. As a sysadmin and hacker, he gets to write elegant code and then try to make that work in the real world. He started Acme Gating to provide Zuul support and services. Zuul is a project that is a gating system that helps you stop merging broken code, makes sure that every change is fully tested and before merging, and tests those changes amongst multiple services, or microservices rather. So I'm going to let the expert here, Jim, go ahead and take it away.
Hi, it's good to be here with y'all. Why don't I share my screen real quick, if that's okay? And so yeah, as Mike said, I'm one of the original authors of Zuul and the current project lead, and Zuul is a project gating system. And I guess the first and obvious question is, what is a project gating system? Is it a CI system? Is it a CD system? And to that, I would answer yes, it is. But I see sort of the world of CI and CD as a continuum. And the first CI systems, if you look at them, if you remember what CI stands for, continuous integration, right? The first CI systems were you would merge a change to your Java project, and you would run the build after doing that and see if the build broke. And basically, this was post-merge testing. This is testing that was focused on the past. Things have moved a bit since then, and we have pre-merge testing now. So you write a change, and a CI system tests that the change that you wrote works before you merge it, which is great because you can find out that you can find out that it's broken before you've broken it for everybody else. This kind of testing is focused on the present. So I think gating is the continuation of this, and it's a future-looking system. It's about saying not only, does the change that you just wrote work? It's does the change that you just wrote work when it's going to be merged with the tree, which might have moved on since you wrote it. Other people might have merged changes since then. Does it work with all of the other changes that are in flight? You know, your colleagues are writing changes at the same time you are, and you may or may not be talking to each other. When those all get sequenced up to merge, is the thing still going to work? And does your project have dependencies that, is it going to work when this dependency changes? So that's how I see the purpose of a project gating system. Is it's CI and CD that is focused on the future. So a quick little bit about Zuul's development history. How did we get here? How did we end up thinking that we needed to make?
Jim, sorry to interrupt you, but do you mind turning your video back on? The video is actually shown in the stream.
Oh yeah, let's see. How do I? Can I share? I'm not actually sure if I can share the video and the screen at the same time.
You should be able to. It's
so
normal.
if I share,
maybe do 2 connections.
oh,
No, you shouldn't have to.
I have to.
Yeah, it's normal for Zoom if you don't specifically turn the video off. So you turn the video off. So don't turn the video
oh
off.
wait,
And then
there,
share it.
okay. So
Yeah.
all right, yeah. When I shared, it turned the video off, but then I
Okay.
can turn it back on. It looks like.
Cool. Okay.
Okay, so we've
There we
got a slide, and we've got me now.
Perfect.
Okay,
And the
great.
rest of us actually.
Great. Cool. So yeah, any questions so far while we're
There is a question, but I want you to get past the intro first.
Okay,
So people have
yeah.
sort of context.
Okay, so how did we end up thinking that we needed a system like this, right? Why couldn't we just check to see if our build was broken every morning? And so Zuul came out of the OpenStack project. We started working on Zuul fairly early on in OpenStack development, and the reason is if you look at this slide here, I've got a lot of logos on here. None of those are actually the OpenStack logo, and that's because when we present OpenStack sort of to the world, we talk about it as a single product, but really underneath it's a bunch of independent projects, semi-independent projects that are trying to work collaboratively to build a cloud system. And so each of these little logos here is representing one of those projects. And one logo in particular is I think near and dear to one of our panelists today. These I guess the problem that we were presented with is how do we develop all of these projects together and make sure that that we can, every 6 months release something called OpenStack where they all work together. And so that's kind of why we ended up with developing this system that was focused on testing changes before they merge and testing them with other projects, dependencies, and other projects, that sort of thing. So that's sort of where Zuul came from and why we started to go down this road in the first place. A key aspect of how Zuul does its work is something called speculative execution. We didn't invent that. Speculative execution is a pretty important concept in computer science and computer engineering. And the idea is that instead of just, it's basically about saying, what's going to happen in the future if these things happen, right? So in processors, you've got branch prediction, where processors try to anticipate what are the next few instructions going to be, and if they're right, then they've saved time. If they're wrong, then they discard their results and they start again. And so that's actually something that Zuul does, is it anticipates that changes are going to merge to other projects and incorporates them into its testing. So we've got two little graphics here on the left. It's kind of illustrating how you can use this with dependencies. So you could have a front-end UI change that depends on a back-end server change that depends on changes to underlying libraries. And you can build up this sort of speculative chain of what is going to happen when all of those changes merge. And then on the right is a illustration of how Zuul sequences those changes in its testing, right? It takes the latest merge change, and then it builds on top of that. It says, I need to test this change that somebody wants to merge, and I need to test these 3 other changes that depend on it, right? And if one of those fails, it pulls it out of the sequence and keeps going. So that's a pretty central concept to how Zuul does its work. And
how do you track which changes depend on which other changes?
Yeah, so that's a good question. There's a couple of ways that that we did that. One is there's of course Git dependencies, right? So you actually if you're in GitHub, you'll see this as a series of commits in a pull request, right? If you're in Gerrit, then each commit gets its own change, but it still recognizes the Git commit hierarchy. And the Git dependencies are immutable, right? Like you can't pull one of those out. You have to merge all of those changes. But that is part of the dependency sequence. Another is the implicit sequence of changes that happen when people approve them for merging, right? So I guess an important part of what I think belongs in a gating system that I may have glossed over is that the gating system is doing the merging, right? So there's no person pressing the merge this PR button on GitHub. The gating system is responsible for doing that because it's also responsible for determining, at the moment of merge if the change passes tests or not. So when people, if they're in GitHub or Gerrit or whatever, and they're reviewing proposed changes and they say, yes, I want this thing to merge, they do something to indicate to Zuul that they want it to merge. So in Gerrit, you leave, actually in both, you leave some kind of approval on the change or the PR. And Zuul kind of takes it from there. And so you can imagine that as you're going through your day and you're saying, oh, I want this to merge. This one needs more work. Go and make a change to it. And then maybe you find a couple more changes that are ready to merge and you approve them. Zuul is going to start sequencing those as you approve them. So there's this implicit ordering based on that. And that's actually kind of an illustration of what might be going on here on this slide, right? So perhaps somebody approved a Nova change, 2 Nova changes in a row. That Nova is an OpenStack component, right? There's another OpenStack component called Sender. Somebody else might have approved that. But these projects are both OpenStack projects. They need to be tested together. We need to make sure that Nova change isn't going to break that Sender change and that sort of thing. So this implied dependency sequence is kind of the next thing, and that's how you end up with these sequences of changes. Looking at Zuul here, the third thing is, I think, the most powerful way of sequencing dependencies, and it's interesting because it's actually not something we started with in Zuul. It was really an emergent behavior, but now we see it as absolutely critical to it, and that is explicit dependencies between changes. And so that's the idea where, I guess going back to this thing where you have a front end change and you say as part of the commit message, this change depends on the back end change. And so not only do your reviewers see that when they're looking at the commit message, but Zuul sees that and it incorporates it into its sequencing system. And if you want to indulge me for a minute or so, I actually have a sort of walkthrough for what that looks like if folks would like a little visual illustration of that.
Yeah, I think so.
Yeah, that'd be great.
I don't know if would it be time for the first question? I think it might be.
Yeah.
So somebody actually asked from the YouTube stream. They're curious if you'd be willing to compare Zuul and GitLab CI, depending on how much you know about GitLab CI.
Yeah. So GitLab CI is pretty powerful. If you look at the merge trains feature in GitLab CI, that certainly has some it kind of echoes somewhat of what I'm talking about here about the relationship between changes and particularly the sequencing aspect. I think one of there are two things about Zuul that I think make it really kind of a standout system, and one is it works with a lot of different code review systems, and it works in a lot of different cloud environments. So it's actually great for bridging across projects that might be in Gerrit or GitHub or Pagure or GitLab. All of these, we've got support for all of these in Zuul. We're still working on the GitLab driver, but that's work in progress, and as well, it supports a lot of different cloud environments. So Zuul's execution can be, not only in you can run it on a container system. So you can run Zuul jobs in Kubernetes or in OpenShift. You can also run them on VMs in any number of public clouds or private OpenStack clouds and that sort of thing. So there's really a breadth of what you can use Zuul for as compared to some of these other systems. And I think this sort of explicit dependency thing that we're sort of dancing around right now is another really key unique feature.
Awesome.
Lal, does that answer your question?
About a 7-second delay. So
Yeah, well, we'll pick him up later on, or we'll
Okay.
pick them up later on, and if they have follow-up questions.
Yeah. So yeah, why don't I talk about that a little bit more? So I've contrived this example, and I've intentionally made it not OpenStack specific. Hopefully, this is something that everybody here can relate to. So I've got these 3 logos here because I apparently like slides with logos. But with these logos, how can you not love them? So over on the left, we have the logo for Sender, the OpenStack Sender project. That's OpenStack's block storage system. And in the middle, we've got Gopher Cloud, and the right, of course, Kubernetes. And the example that I'd like to walk you through here is this idea that we want to add a new feature and expose it through this entire stack. So let's add support for secure delete in Sender, and don't focus too much on the details here, because this is a synthetic example, and I'm just trying to create something that sounds plausible. Whether or not we could actually do this or need to do this, I don't know, but to me this seems plausible, right? So we want to expose the idea of doing secure delete when block devices are removed from Sender, and we want to make that happen in Kubernetes when, say, you've got a persistent volume that gets deleted. You want that PVC to cause the underlying Sender API to do the secure delete, right? So this is a new feature that we have to move all the way through that entire stack. So we'd start by uploading a change or writing a change to Sender and uploading it to OpenDev's Gerrit. OpenStack uses a Gerrit code review system that's hosted by OpenDev for its changes. So this is what that looks like. This is basically a change that's in review. We've got the commit message here on the screen where we're adding the API option to perform secure deletes, right? So the next thing that we need to do is add support for using that API to Gopher Cloud, right? So we open a PR against Gopher Cloud, and that lets the world of Go access this Cinder API. And then finally, in Kubernetes, we update to the latest Gopher Cloud and have it use that secure delete option when Cinder or when volumes are deleted. So at this point, we've got 3 changes out there. None of them have merged yet, and we can test all of them independently, but there's no relationship to each other. We don't. The people reviewing the Kubernetes change, they're kind of taking it on faith at this point that everything else works. They see this PR show up and say, "Hey, we totally added this API to Gopher Cloud. We're pretty sure it's going to work. Please merge our change." So maybe we want to use Zuul to show that this entire sequence can actually be tested together. So we go back to our Kubernetes change and we add this depends on footer to the change, and you can see that it says depends on, and then it's got the URL for the Gopher Cloud change. And so this is how you do that explicit dependency specification in Zuul. We just made it URLs so that you can actually support cross. We call them cross-source dependencies, where you have changes in GitHub depending on changes in Gerrit, right? So anyway, this is the Kubernetes change saying I depend on the Gopher Cloud change. The Gopher Cloud change depends on this change to Cinder. And if we go back to, so at that point, so I just want to highlight again the depends on here. It's a depends on to a different system. So we're not even saying we depend on another GitHub change. We're actually depending on changing Gerrit. But that's okay. Zuul knows about GitHub. It knows about Gerrit. It can stack those 3 changes up, and this starts to look like that diagram earlier. We've got these 3 changes, and the little lines show the connection in Zuul. By the way, this is what the Zuul status interface looks like. It actually shows you this relationship. So that's how you stack those up. We can extend this one step further, though. This is a brand new feature, and perhaps our Zuul doesn't actually have a job that exercises it yet. And so we can extend this idea of speculative execution where we're saying, Zuul, I want you to run my tests with these 3 other changes. We can also say to Zuul, hey, I want you to run a job that you've never seen before. Zuul's configuration is in YAML files, of course. And so this is what a Zuul job definition looks like. So if we wanted to add a job that says, exercise the Cinder secure delete option with Kubernetes, we can call that job Cinder Kubernetes secure delete. We can parent it on a job called, say, DevStack Kubernetes. DevStack is OpenStack's environment for performing development, right? So it's kind of like Minikube for OpenStack. So you can imagine that there's a job somewhere in the system that sets up a DevStack for testing OpenStack and sets up a Minikube for testing Kubernetes, and maybe does both of those things for testing the 2 systems together. Zuul has a really powerful inheritance system for its jobs, so we can actually take you can spend a lot of effort setting up a job that sets up your infrastructure and then make a bunch of little jobs that make small tweaks to that. And so that's sort of what we're doing here. We're saying, let's take that DevStack Kubernetes job and just add on to that a little bit to test our secure delete system. Underneath this job definition, we've got the project definition where we say, I want you to run all the unit tests, I want you to run the functional tests, and I also want you to run this Cinder Kubernetes secure delete. So if we wrap all of that up into a change and upload it to to Garrett, then in Zuul, now we've got a sequence of 4 changes, and the last one runs that extra job that we just defined. And when that's done, it'll report back to Garrett, and you can actually see on the bottom of the screen here the little Cinder Kubernetes secure delete job succeeded. So, so that's it's kind of a whirlwind walkthrough, and it's high level, but that's how you can set up these complicated series of changes across different projects and see results, see functionality changing in your dependencies before any of these changes merge. So, in this example, nobody had to actually merge a change to see this job run to completion and exercise our new feature. And that's a really powerful tool, and we use it all the time to test changes between OpenStack projects and between dependencies for, external dependencies as well.
Now, Jim, at this point, if we workflowed this, it would then test this new merge and patches against all of OpenStack if it was an internal OpenStack type deal.
Yeah, and it's one of those things of like what's the test area that you want to cover, right? We can there's sort of in OpenStack there's this core set of projects where we kind of think that Keystone and Nova and Sender and some other things that kind of they're all really tightly interrelated, and we need to make sure that they never break each other. And so we're always testing those projects against each other. As OpenStack has grown over the years and as its interactions with other communities have increased, the surface area has gotten huge, right? And so, early on, we were testing as much as we possibly could all the time. That kind of grows exponentially, and it's ultimately not sustainable to test everything. And so we've gotten better about saying, these things we always need to test. This thing we only need to test some of the time. When this part of the system changes, that sort of thing. So yeah, if we added the workflow vote on this to approve it, we would certainly be merging this change only if it passed the new test that we added. We might not want to always run that change though. We might not always want to run that test, and so we then might make that contingent on, let's only run this job if we're touching the part of Sender that's relevant to secure deletes and that sort of thing. So, and the other thing to know about the workflow here is that because of this dependency chain that we've made, this change isn't going to merge until the ones ahead of it have merged. So since we depend on that Kubernetes pull request, we're not going to merge this until that one passes. And that one's not going to merge until the Gopher Cloud passes. And the Gopher Cloud one isn't going to merge until the Cinder one passes. So, not passes, but merges, right? So we can maintain that strict sequencing to make sure that not only can we prove out that this whole new feature works in advance, but we can make sure that we don't merge any changes that depend on it until the dependency changes have merged as well.
So can you accidentally get a circular dependency? Has that happened in the past?
Circular dependencies are a really interesting thing. With Zuul, we started off with a pretty strong stance against circular dependencies because we wanted to make sure that the continuous deployment of an OpenStack cluster always worked, right? And so we wanted you to be able to upgrade your Nova nodes and then upgrade, or maybe upgrade Keystone first, and then upgrade Nova to use a new Keystone feature, and so forth, right? So we said that we couldn't require cloud operators to shut down their entire cloud and then bring everything up again. We had to make stepwise upgrades, and so we mirrored that in Zuul. We made Zuul enforce that by saying you can never create a circular dependency. It always has to be what we call a DAG, right? It's just like Git. It's a directed acyclic graph. It always has to be a strict tree structure, and you can't have a cycle where one thing depends on another. That worked out really great for OpenStack, but this is also kind of one of those. It's an illustration of how we as a community have evolved over the years. As more people who aren't OpenStack started using Zuul, they said, we don't have that restriction. In fact, our software works a lot better if we don't do that. We're doing things like, so some of the other Zuul users now are in like in the manufacturing space. We have automobile manufacturers, embedded systems manufacturers, stuff like that. And they're like, we don't have that upgrade cycle. If we're upgrading the firmware on a car, we kind of do the whole thing all at once. We don't just upgrade the entertainment system and then do a stepwise upgrade of the transmission control system, right? Like that doesn't make any sense. So they said circular dependencies are really important for us because that is how we do our development. And so we've actually added the ability to do circular dependencies, and they work kind of like how you'd expect, or how you would, as you suggested, accidentally do, right? Where you stick this depends on header and change A that points to B, and then do the same thing in B that points to A. If you do that, Zuul will recognize that that is a circular dependency, and then it actually changes its algorithm a little bit. It says, I'm not going to do a strict ordering between these. I'm going to recognize that all of the participants in this cycle need to be tested together, and then merged or not merged as a unit. So it's still kind of, the graph that Zuul makes still kind of looks like it normally does, except that there's potentially a grouping of changes that behave, that move together, and all of the changes in that group have all of the Git changes checked out for them at the same time as well. So I think that for me, to kind of sum up this line of thought, Zuul is a tool that lets you ask what if, right? It's about saying, what if I merge this change? What if these two changes that depend on each other merge? What if this other dependency merges? Like what's going to happen in that case? And I think that's where the power comes from. I mentioned some of these other. We've been talking about OpenStack and Kubernetes a lot, right? So these are some of the other Zuul users that are out there. You can actually on our website, a lot of these users have stories posted there about how they're using Zuul. So if you want to read about them, OpenLab is an interesting one here because they perform sort of cross-community testing. They're really at the heart of what I've been talking about. They do cross-community testing between OpenStack and Kubernetes. So they're, if you were to do this whole sender secure delete thing that I was doing, that's probably the most likely place for that job to run, because they're doing that kind of testing today between OpenStack and Kubernetes. But yeah, we've got a lot of different folks here using it for a lot of different kinds of development, which I think is really interesting and exciting. So. And these are some places you can find out some more information about Zuul. We've got a website at zuulci.org where we've got docs, link to our mailing list, our IRC channel on Freenode where you can chat with us and that sort of thing. The docs have instructions for getting started, so you can get a Zuul up and running pretty quickly. You can also look at opendev.org, which is a very large public Zuul system. So that's where OpenStack. That's what OpenStack is using for its development. So you can kind of see it in action there. You can see the example jobs that we've got, the standard library of jobs, so that if you do use Zuul, there's a whole community of folks working to make reusable jobs so that you don't have to start from scratch. And then we've got and this is one of those things where, for me, it almost goes without saying, but I should say it. And I can't believe we've gotten this far without me actually saying the words open source. Of course, Zuul is a community-developed open source piece of software. We're not driven by one company. This is actually a bunch of people working for a bunch of different companies, as well as some people working on their own time, contributing to make this thing better. So anyway, yeah, it's open source. You can download and run it, and there's also commercial support and hosting offerings that you can find out on the website. And
awesome.
If we
if that's it for the slides, you can stop share. Oh, actually, you've got
So that's it for the slides. I'm happy to. This is probably a great time to stop for questions if there are any. But if not, I can just sort of show you some of, like I said, just show you what's going on opendev.org live right now.
I'm curious, what's the technology stack within Zuul? What's it written in and with?
Yeah, so it is written in Python, and it's actually kind of it's a sort of microservice architecture, and so it's a bunch of different Python services that work cooperatively. So there's a web service, there's a scheduler that does all of the deciding, what to do with what jobs to run, that sort of thing. And then the executors are they're our most important scale out feature. So one of the pain points early on actually was as OpenStack was growing exponentially, we had to scale our CI system to match it. So we actually the execution component of Zuul is a scale out component as well. Slow computer. There we go. So if we look at this is the Grafana instance for OpenDev, and if we look at it, we can see down here. Where are they? Yeah. Okay. So these are the. It looks like we've got 12 executors online right now for OpenDev. So that's 12 servers that are just responsible for running the jobs. That's not 12 test nodes. That's 12 machines that are running the test jobs on the test nodes. Right now, we're using, let's see, almost, was it around maybe 900 test nodes right now. So these are about 800 or 900 virtual machines that are in use right now, running tests. So yeah, the stack internally is Python. And like I said, microservices for scaling out. We, at this point, we're kind of agnostic about whether you run Zuul itself in containers or not. You can install it on a bare server or a VM or whatever in the way that you would normally install a Python program. But I think at this point, most of the larger Zuul installations are running in containers. Some of them are running Zuul inside of Kubernetes. Some of them are just running it inside of Docker, using Docker Compose, that sort of thing. But that seems to be the way what people are moving to. And it's really nice because we build container images not only on every release but every commit. So it's pretty easy to just run the exact container images that we're running in OpenDev for Zuul's own Zuul. Let's see. Another important thing to know about the tech stack is how the jobs are written. They are written in Ansible. And that's because Zuul is a multi-node aware system. So, with some CI systems, they've got the idea of one test node down for running a job, right? But if you wanted to, say, you're doing work with Kubernetes and you wanted to actually stand up a full 3-node Kubernetes cluster, with Zuul, you can do that pretty easily. You can ask Zuul for 1 node. You can ask Zuul for 3 nodes for your job, and Zuul will happily provide you, 3 virtual machines or 3 containers or whatever it is that you ask for. But if you think about writing a job that uses multiple nodes, you kind of need an orchestration system. You need a way of saying, I want you to run this on node number 1, and then I need you to run this on node number 2, and this other thing on node number 3. And so we needed a system for saying, I want to run scripts or programs or something on arbitrary remote nodes. And there was this great system called Ansible that was developed just for doing that. And so we said, well, rather than reinvent the wheel and create our own orchestration system for doing CI on nodes, we said, let's just use Ansible. So what you get as a Zuul job author is you write a playbook and Zuul sets up the inventory for you with the nodes that it gets, and then it runs your playbook against that inventory. So if you know Ansible and you like Ansible, then that'll be really familiar to you. If you're like, oh well, actually, I don't want my CI system to be opinionated about what how I do my deployment, that's fine too. Ansible, as it turns out, is really good at running other stuff. So if you just have a shell script to do whatever it is that you need to do, that's fine. You can write 2 lines of Ansible that say, run this shell script on the test node, and you're done. You've escaped Ansible, and you can do whatever you need to. So yeah, I think that's the highlights of the tech stack there. There's an SQL database, can be MySQL, MariaDB, Postgres, PostgreSQL. They're all supported. And then sort of behind the scenes, we have a Zookeeper system for helping those components communicate with each other. But those are all kind of behind the scenes details. As a Zuul administrator, you might need to know that they're there. As a Zuul user, you don't need to know that they exist at all. So yeah, this is the current utilization of Zuul on OpenDev, and this is the actual web interface for Zuul. So if we go look at Zuul is a multi-tenant system, I should say. So starting here, we're actually looking at all of the different tenants that we have in Zuul. We've got OpenStack, which is our largest tenant. We have Zuul itself. We have some Python projects. The cryptography and the packaging folks have some projects in the system, because we're actually all of the communities involved here are heavily dependent on these Python packages, and we want to make sure that this is going to that cross-community testing that I was getting at earlier. We want to help the Python community make sure that that they're able to test on all the platforms that are important to them and are important to us too. So we actually have some ARM testing going on for these projects down here. But I'm going to hop over the OpenStack tenant real quick and just show you what a fairly busy Zuul system looks like. So again, this is live, so I don't really know what to expect here. This is what happens. The check pipeline is what happens when people upload changes. So this is kind of before they've when you write a patch and you upload it for the first time. This is when we run the initial test. I've even not gone through code review yet or that sort of thing. So I'm going to just actually go ahead and expand by default here. So if we look at this, there's a bunch of in progress. Some have succeeded. These jobs are paused. All of these jobs are running for this change, right? So each of these little boxes here is a change to a different project in the system. And then if you expand that, you can see jobs that have all of the different jobs that we run for that change. So a bunch here have succeeded, some have failed, some are still running. This is a long series of changes, right? So here's a change that depends on several others. If this should start looking exactly like that slide that I showed you earlier, and this is exactly how we represent it in Zuul's status interface. So these lines between changes are dependencies, and then the gate pipeline is where we changes that are about to merge, right? So here's a queue of 2 related changes to airship projects, right? So this one's going to merge first. This one is being tested with it in sequence. And I actually don't know if this is a git commit dependency or just a dependency that's formed by the approval sequence, or it depends on or what. We'd actually have to go take a look to figure that out. But regardless, right now Zuul considers that they are dependent on each other, and so this one's being tested with one ahead of it, and that's happening in parallel so that they merge more quickly. These two are sharing a queue, but you can see that this one, the one at the top here, has failed, which means that Zuul has decided that this one no longer depends on it. So we're still running the jobs on this because we want to, we've sunk a lot of time into running these tests already, and we want to report back to the user as much information as possible. So we're going to keep running the jobs until everything's done. But in the meantime, as far as Zuul is concerned, this change is now the next one that's going to merge, assuming that everything passes. So no line connecting these two is how we determine that Zuul has pulled that out. So yeah, that's.
Do you want to actually click on one of those? I'm curious what this looks like in terms of, like, say if I'm a developer, like actually particularly into a failed test. Particularly if I'm a developer trying to debug the failure, what this looks like.
Yeah, so let me click on 2 things. One, just while we're here, this is
If you click on that OpenStack Ansible one, I'll look at it from a core perspective.
Oh, okay, great. Yeah. Yeah, I just wanted to show you the streaming console output that we have. So I mean, it's kind of a standard feature, but if you like to watch console logs, we've got that here.
What's handier is that regex search.
Yes, yeah, like fail,
right?
Type fail, yeah. So yeah, that's pretty cool. So that's one tool that if you see that something is failing, you can and things are still in progress, you can check on it while it's running. Okay, so where was the Ansible one? This one
Look
here.
farther down, yeah.
The one in so do you see
We
one?
just and we just added some support for the latest CentOS and Ubuntu. So and also I think Debian.
Should I try this one then? The Ansible deploy AIO metals into okay. All right, so we'll
and to be honest, sometimes we just recheck and we go through.
So actually, yeah. So we're actually kind of at a awkward place here in that because Zuul is still running this job, we can access. Yeah, we can access the logs, right? So we've got the logs here in our log storage system. So you can see the job output. There's a whole host, like we collect a whole bunch of logs when we're doing this. I kind of want to show you the what it looks like when it's finished reporting, because frankly, because it's easier to use and more. There's some neat features there. So I'm just gonna look for that same job and see if it failed recently, and we'll look at that instead. Okay, so basically, as long as the change is still in progress, which is what we've got here, right? We're still running which one? We're still running this job, which means Zuul hasn't, like, it's not final yet. Zuul, it's clearly not going to merge, but it hasn't. Zuul hasn't made a definitive determination because all of the jobs aren't finished yet. So it hasn't yet reported back to the code review system the final results. Things could still change. So that's why in progress we have access to the raw logs, but we don't actually have a final result yet to look at in Zuul. When it reports back to the code review system, this is the view that you get, right? And so there's actually a nice screen that shows you the summary of the build, when it started and finished, and the branch, the project, the pipeline, some other stuff. We do this thing where we, because the jobs are written in Ansible, and Ansible is a series of tasks, we can actually look at the first task that failed and show it to you with the assumption that maybe there's something useful there. So this is the Ansible task that failed, and this is the last few lines of it. So often, as a developer, you can hop onto this this build summary page and actually just see the error that tanked your job right there. This doesn't mean anything to me. I don't know if it means anything to you, Amy.
It kind of looks like the container didn't build properly, which is why sometimes recheck works for us, because we're a deployment project. So if the containers or the VMs didn't deploy properly, we'll sometimes fail just from that.
Yeah. So this is the I'm feeling lucky thing in Zuul, right? You can look at this and maybe this will just point you right at the error and you can go and fix it. We've got all of the logs so this is the slightly more attractive version of that raw log storage that I showed you before, right? So we've got all of these ETH tool config files, things about things on the host, and this is something that we've learned after years in the trenches in OpenStack development, right? This job took an hour to run, and my goodness, after the end of that, if it's failed, you sure want to figure out why it failed, right? So that's why we collect so much log information, so that when something goes wrong, hopefully we've got everything that a developer needs to figure out what that was, and they can go back and see everything that happened. If the Zuul has this artifact system, so you might, this particular job doesn't have a lot. We've just got this script to download all of the logs and then the Zuul manifest itself. But examples of other artifacts that we have are documentation builds, preview sites for documentation. So if your job builds documentation, you can just add a link here, and then developers and reviewers can click on it and see a preview of the doc build. Container images, tarballs, things like that, you can stick here as well. And then finally, we have a view of the that's a big one. A view of the tasks in the Ansible playbook that make up the job. So this is the really big thing that I'm going to hide. But if you look at this, the job is made up a bunch of playbooks, and each of those have tasks, and you can kind of drill down into each of these tasks and see what's going on. So this particular job has one really long task in the middle that produces a lot of output, which is I guess you can scroll through it all if you want, but so anyway, that's those are some of the tools available to developers when they look at failures like this.
So folks have different kinds of learning methods. I'm curious, are there any ebooks or anything available for folks out there to learn Zuul, or what's the canonical source of info for folks to go grab?
So I would go to zuulci.org, and I don't think we have an ebook at this point, but we let's see, we've got if you've watched this, you've probably already seen everything that's in this video, so that's kind of a short version of what I was doing earlier. If you go to the Get Started page, we've got a tutorial. So this will get you up, and so if you're a hands-on sort of person, this will get you up and running just on your local laptop or workstation or whatever, using Docker Compose. So this will bootstrap an entire Zuul system using Docker Compose, and you can play with it there. We're actually in the process of expanding this tutorial system now, so that you'd start with this and then build on that for other tasks.
Awesome.
There are some other parts of the Zuul documentation that kind of tackle this from different perspectives. So, if you just want to read more about Zuul concepts and things like that, we've got discussion sections there. And I think there are, some videos on YouTube of conference presentations and things like that. And finally, there is a Zuul from scratch section in the documentation as well. So it's kind of the opposite of the quick start, whereas the quick start is like, just get me a Zuul up and running so I can play with it. If instead you are more of the, no, actually I wanna start with git clone and go from there. You can do the Zuul from scratch thing. So yeah, I'd love to have more of the ebook style stuff, but we do have a couple of different styles of approaching this.
Awesome.
Yeah.
No, that's great. I mean, you can turn a web page into an ebook if you really want to. So that's awesome. So thank you very much for this overview and dive into Zuul.
Oh, you're quite welcome. It's been great to talk with you about it.
Awesome. Mike, Josh, Amy, anything else?
No, I have other questions, basically having worked on the Kubernetes project and Prow. Where once again, I'm looking at this and saying, we didn't learn nearly enough from Zuul.
Yeah.
Although our biggest challenge is we have looked at the sort of multi-project dependencies, and our biggest blocker there is running out of cloud resources to actually run the tests.
Yeah.
Because given microservice architecture, there are more projects in Kubernetes than there are in OpenStack. The projects are smaller and there are more of them. But that could go on for quite a while, and we're at time.
Yeah. No. So thank you very much, James, for coming on. Really appreciate it.
Yeah. Thank you for having me.
Very informative.
Thank you.
Thank you.
And without further ado, we'll see everybody soon. Coming up tomorrow on the channel, we will have an OpenShift Commons briefing about cloud native network functions. So if you're curious about the telco space, which I know some of these people on this call are, tune in and we will discuss.
Yeah.
So,
and then in 2 weeks for Cloud Tech Thursday, we will have the folks from CERN. Actually, Amy, you should plug this.
Yeah, we'll have Belmero, who is coming to talk to us about scaling at CERN on OpenStack. So that'll be a really good talk because they're the largest user of OpenStack in the world.
wow.
So yeah, we're kind of two OpenStacky related things in a row. I personally take Zuul for granted because I use it all the time. So it was really great to get some more of the history and some of the more in-depth usage, which I'll go and use daily now. So I really appreciated this, Jim. So yeah, we're looking forward to having everyone in 2 weeks and spread the love about Zuul.
Yes, please share this
Thank you.
video out with folks who you see might need it. So thank you.
And stop merging broken code.
That.
Best tagline ever.
Yeah.
All right, y'all. Take it easy. Be safe out there.
Take care, all.